Hello, ladies and gentlemen. This is Mr. Cunningham, and what we're going to be talking about today is in lesson 12.1, which we're going to start talking about gases. So today, make sure you take some time right now and complete that bell work problem over like drawing a sketch of gas particles and writing a little description about it. Go ahead and take some time to do that. Again, there's no really right or wrong answer. I'm just trying to get you to think about what gas particles look like and kind of jog your memory. All right, now that you've done that, what we're going to be doing today is we're going to learn about gas particles, some of the properties of gases, and so here are your objectives. Here's what you should know by the time you finish watching this video. So sub-objective 1, you should be able to know the properties of gases and know the properties of gases that we can measure. Sub-objective 2, be able to convert units of pressure, volume, and temperature. All right? And our goal, okay, our overarching thing, the thing you should be able to do is understand how pressure, volume, temperature, and quantity are all related to each other. So let's go ahead and get started. So as we start talking about gases, the first thing we're going to talk about is the properties of gases. All right, so first thing, gases are considered to be fluids. All right, I know that you may not think that they don't look like that. They don't feel, I guess, like wet or damp, but they are actually considered fluids. Things move through air just like they move through water, so they're actually both considered to be fluids. Gases have very low density. When it means having low density, it means low mass per volume. All right, there's not very much mass in a large volume for gases. Gases are highly compressible. We can push them into smaller areas. That's what compressible means. Gases completely fill their container and take its shape, just like a balloon. All right, completely fills the container, takes its shape. A basketball, gases completely fill a basketball, take the shape of that container. Gas particles are in constant motion. Okay, they're flying around each other, bouncing off of each other, and the movement of gas particles is rapid, it's random, and it's straight. All right, so particles move in straight lines, they bounce off of each other, they bounce off the walls of their container, and they're moving very quickly. So here are the 4 properties of gases that we can actually measure and that we're going to be focused on measuring in this unit. The first one is pressure, all right? The second one is temperature, third is volume, and the last one is quantity. So pressure is a measurement that is a measure of the amount of what we call bombardment, or in other words, it's the amount of collisions. All right. Temperature is a measurement of energy. All right. How fast are those particles moving? We would even call that kinetic energy. Kinetic energy is the energy of movement. That's what temperature is a measure of. Then volume. Volume is how much space these particles have to move around in. Then you've got quantity. Quantity is the number of particles. How many are there in a certain space? These are the 4 properties we're measuring, all right, that can be measured with gases. Here's what they are kind of measurements of. And then we're going to start looking at what are their units. So the units of pressure are going to be in atmospheres. Now there's tons of different units of pressure. You've probably heard of like PSI, which is pounds per square inch. You've heard of tons of pressures. The one that we're going to typically be working with is atmospheres, also abbreviated ATM. Then we've got energy. Energy is measured in Kelvin. Now you might be like, wait, what? What's Kelvin? Well, Kelvin is another temperature scale, just like Fahrenheit and Celsius. In science, we use Celsius a lot, but whenever we work with gases, we always have to use temperature in Kelvin. Then the next thing is volume. Volume is going to be measured in liters. Again, sometimes we often measure volume in milliliters. There's tons of different other units for liters, or excuse me, for volume. Then quantity, we're going to be using moles, which shouldn't be a surprise to you. We've used moles in the last 2 units we've been working on. We're going to continue to use them. Moles are a staple of chemistry. So those are the 4 properties that can be measured with gases and the ones we're going to be focused on. So the first one we're going to look at of those 4 is pressure. Okay, the pressure of a gas is proportional to the bombardment of the molecules on the surface of the container. So when we say it's proportional, it means if your pressure is high, that means there is a lot of bombardment. There's a lot of particles hitting the outside of the container if it's a high pressure. If it's low pressure, that means there's not very much bombardment. There are not very many collisions, all right? So when you think of pressure, think of bombardment, think of collisions. Air pressure, all right, we're going to define kind of two different terms here. Air pressure is the bombardment of the molecules in the atmosphere on every exposed surface. So right now, your body is experiencing air pressure. There are particles hitting the surface of our body at all times. Now you might be like, I don't feel that. Well, you're used to it, all right? It's because we are under a certain amount of pressure from our atmosphere, and we've grown accustomed to it. The other type of pressure we're going to talk about is gas pressure. Gas pressure is the bombardment of the molecules in a sealed container on the walls. So it's kind of like the pressure from the inside pushing out. So here's kind of an example of gas pressure and air pressure. Air pressure is particles on the outside of the container hitting on the outside. Okay, that's air pressure. Gas pressure is the pressure of molecules hitting from the inside towards the outside of the container. All right, both of them are making collisions. Air pressure is on the outside, gas pressure is on the inside. So what I want you to do is take a moment and sketch that on your notes, just so that you can kind of get the idea of what gas pressure and what air pressure is. So the next things we're going to start looking at are units of pressure. Now, there are a lot of units of pressure. All of these types of pressure are units you could experience. The one that we're going to be working with the most is this one, is atmospheres. Now, that doesn't mean that in a problem it may not give you, this is called millimeters of mercury, this is called inches of mercury, this is PSI, which stands for pounds per square inch, this is kilopascals, all right? So all of these units are ones that you might work with. Now, here, all of these things are equivalent to each other. So let me explain that a little bit. 1 atmosphere of air pressure is the same thing as 760 millimeters of mercury. So in other words, remember how we worked with conversion factors and stuff like that? We could write a conversion factor for atmospheres to millimeters of mercury. Okay? 1 atmosphere is equal to 760 millimeters of mercury. They are equivalent to each other. All right? Then the next one would be inches of mercury. So in other words, 1 atmosphere is also equal to 29.92 inches of mercury. 1 atmosphere is also equal to 14.7 psi. 1 atmosphere is also equal to 101.3 kilopascals, or kPa. So all of these units are equal to each other. This many atmospheres is the same thing as this many millimeters of mercury. Just like 1 dozen is equal to 12, 1 atmosphere is equal to 760 millimeters of mercury. All right, so one of the objectives for today is that you should be able to convert between units of pressure. So we're going to practice that right now. So if I asked you to convert 3.11 atmospheres to torr, okay, now you might be like, well, what's torr? Torr is on your notes, okay? Torr is actually the same thing as millimeters of mercury. In other words, if I had torr right here, torr is equal to 760 torr. All right, they're the same conversion. So if I said convert 3.11 atmospheres to torr, I'm going to start with my beginning number. I've got 3.11 atmospheres, and I'm going to show you using dimensional analysis. Another way that you can think about it is by multiplying or dividing by your conversion factor. Well, you have to ask yourself, if we're going to use a conversion factor, technically we're using something like this. We know that 1 atmosphere is equal to 760 torr. So we're going to write that as a fraction here if we're doing dimensional analysis. So what unit is going to go on the bottom? Well, since we're starting in atmospheres, that means atmospheres needs to go on the bottom. So when I set up my conversion factor, it's going to look like this. Since 1 atmosphere is equal to 760 torr, and I want to get rid of atmospheres, I'm going to put that on the bottom. So I go ahead and do that. And I would get rid of these units. I would only be left with torr, so I do 3.11 times 760, and I would get this as my amount of torr. In other words, these two pressures, 3.11 atmospheres and 2,363.6 torr, are the same pressure, but we're just converting. Now we're going to do another conversion where we're going to convert from 635 millimeters of mercury to atmospheres. So again, we are going to use similar conversion, different marker here. So I'm going to start with my 635 millimeters of mercury. Well, what is the conversion between atmospheres and millimeters of mercury? Well, remember, we talked about this on the previous slide. 1 atmosphere is equal to 760 millimeters of mercury. So I'm going to write that as a conversion factor. Well, the only difference now is I'm going to put the 760 on the bottom. In other words, I'm going to be dividing by 760. Here I multiplied. Here I'm going to divide. So I would take my millimeters of mercury would cancel out because those units, one is on the top, one's on the bottom. Those units would cancel out. So I would just do 635 divided by 760. And I would get that the amount of atmospheres is equal to 0.835 atmospheres. All right, so that's how you convert units of pressure. Again, just like when we did mole conversions, all that stuff, we're just dividing or multiplying by a particular number in order to get us to that desired unit. So, next one we're going to talk about is temperature. All right, so here's what temperature is. Temperature is directly proportional to the kinetic energy of molecules. In other words, if I have high kinetic energy, that means I have high temperature. If I have low kinetic energy, that means I have low temperature. So typically what we use is we use Kelvin, and the reason why we use the unit of Kelvin for temperature is because it is the only temperature scale that starts with 0. Now you might be like, well, Fahrenheit has 0 and Celsius has 0. Well, Celsius and Fahrenheit can go below 0. There is no such thing as negative Kelvin. All right? 0 Kelvin is the lowest possible temperature that could ever theoretically be reached. So it starts at 0. All temperatures in Kelvin are positive. Okay, so that's why we have to use those with gases. All right? So here is the conversion. Typically you'll be either given temperature in Celsius or you'll be given it in Kelvin. So in order to change from Celsius to Kelvin, you just use this simple equation. If you're given your Celsius temperature, all you do is you add 273. Add 273 to your Celsius temperature, you've got your Kelvin. If you wanted to convert back, you would just take your Kelvin and subtract 273. So, for instance, here's an example of that. If I was at 25 degrees Celsius, but I can't use 25 degrees Celsius because for gases I have to use Kelvin, I would just add 273. So I would say, okay, my temperature is 298 Kelvin. Okay, no degrees, I would just say just Kelvin. That's the temperature. All right? So the next one is volume. All right? The volume of a gas is measured in a lot of different units. Typically the one we're going to use is liters. All right? That doesn't mean you can't use milliliters, but typically liters is the one we're going to get to. So to convert between milliliters and liters, what we're going to do is we're going to use this conversion factor. So in other words, 1,000 milliliters is equal to 1 liter. So if I asked you to convert 456 milliliters to liters, well, I'm going to use this conversion factor. So since milliliters are my unit on the 456, what I'm going to do is I'm going to set up my dimensional analysis, and again, you ask yourself, which thing goes on the top and which goes on the bottom? Well, since milliliters is my unit here, and I want to get rid of that unit so I can get to liters, then I'm going to put that number, my 1,000 milliliters, on the bottom. So my conversion factor should look something like this. So I'd take 456, I would divide by 1,000, my milliliters would cancel, they would disappear, and the only unit I would be left with is liters. So the unit of changing from milliliters to liters is I divide by 1,000, and I would get that my amount of liters is 0.456 liters. Let's say that I was now going the other way. Now you might be like, well, that's just easy. I'm just going to do the opposite. And that's exactly right. So if I'm converting from liters to milliliters, all that I'm going to do is flip this fraction. In other words, if I wanted to convert 0.76 liters to milliliters, I would just multiply by 1,000, because now my 1,000 milliliters is going to be on the top. My liters units are going to cancel because one is on the top, one's on the bottom, so I'd get rid of those. The only unit that would be left is milliliters, so I do 0.76 times 1,000, which is going to give me 760 milliliters. So that's our volume property. That's how we can convert from volumes, and that's what volume means. Next one we're going to look at is quantity. Okay, that's our fourth one. So we've looked at pressure, we've looked at temperature, we've looked at volume, now we're looking at quantity. So the quantity of gases, again, obviously we can use like particles, we can use all that stuff. The one that we typically are going to use is expressed in moles, which shouldn't be a new unit to you. I mean, new as in the past few weeks, but this is the unit that we are going to use quantity for, and that is moles. Okay, so now we're going to start talking about, again, your goal for today is that you need to be able to see how pressure, volume, temperature, and quantity are related. So we're going to start talking about those relationships between pressure and volume, between pressure and temperature, all of those four properties, how they're related. So first one is pressure and volume. So think about this. So the more external pressure on a balloon, the blank the volume. So let's imagine that I had a balloon up here and I was going to put more pressure from the outside. Okay, I was going to push in on that balloon. What would that do to my volume? Think about that. Well, that would make my volume decrease, right? It'd be smaller. My volume would decrease because there's more pushing in from the outside, which is going to push those particles closer together. So here's what that means. That means that pressure is indirectly proportional to volume, meaning if my pressure goes up, if I increase my pressure, that means my volume is going to go down. Because as I push more on something, it forces those molecules closer together. All right? Now, this is called Boyle's Law. It's named after a guy named Robert Boyle. It's not important that you know that, but here's a classy picture of him. Next one is kind of some applications of our Boyle's Law. So, if you think about this, if I took a balloon and I took it to outer space, all right? Well, what happens in outer space? What is the pressure like in outer space? Well, there's not very much, hardly at all. We call it a vacuum of space. That's because there's no air particles, no gas particles to apply a pressure. So a balloon in outer space is going to get bigger because there's very little pressure pushing on it. Air bubbles underwater, all right? I don't know if you've ever seen this before, but if you were to take a bubble and put it down at the bottom of a pool and let it rise to the surface of the pool, so rise up 6 or 7 feet or however deep your pool is, what's actually going to happen is, think about what the pressure is like at the bottom of a pool. All right, if you've ever swam down to the bottom of an 8 or 10 foot pool, you probably feel pressure, right? You feel it in your ears probably. That's because underwater, there's more pressure. So as an air bubble rises to the top, rises up to the surface on a pool, what actually happens is it gets bigger as it rises to the surface. That's because the pressure, the bubble started down low where the pressure was greater. As it rises up, the bubble's able to get bigger because there's less pressure on it. Okay, so again, the reasons for a lot of these things is when the outside bombardment, okay, when there's less collisions from the outside, the volume of a substance is able to increase. Next one is temperature and volume. So how are they related? So as the temperature of a gas increases, the volume of the balloon gets what? Okay, so think about it. Let's say that I had a balloon and I had it in the classroom right now. It's probably like in the 70s in here. And then I take it and I go outside, or sorry, let's say we start outside. And it's cold outside right now, maybe 30 degrees. And then I bring it inside. What's going to happen to my balloon? Well, it's going to get bigger. Okay, remember, as temperature increases, what happens to those particles? Well, they start to move faster. When particles move faster, they need more space. They start to spread out, which means it makes our volume bigger. So here's what that means. That means that volume is directly proportional to temperature. Directly proportional means when one thing goes up, the other goes up. So since temperature is increasing, that's going to make my volume want to increase. So what this is called Charles' Law. And again, another classy photo of good old Jacques Charles. All right, so here's some applications of that. Okay, a basketball gets blank when the temperature goes down. Well, think about it. I don't know how many of you have ever tried to play basketball when it gets cold outside, but typically you grab the ball out of the garage, you go to dribble it, and it feels flat, right? And that's because basketballs are going to shrink as the temperature decreases. That's because the gas particles move slower, so they're going to get closer together, which means you're not going to have the same amount of pressure as you're trying to dribble. Again, the reason for this is as molecules slow down, decreasing temperature, they don't push as hard against the container, which causes it to shrink. So, next one is pressure and temperature. So as the temperature of a rigid container increases, the pressure does what? So let's imagine that we had something like a bottle, okay? I don't know how many of you have ever done this. Take a plastic bottle, you seal the lid, you take it, and you put it into a fire. What happens? Well, it blows up, right? That's because as I increase my temperature, my molecules move faster, which makes them want to expand. But my bottle is rigid. It doesn't expand. So eventually enough pressure builds up that the container can't even hold it anymore, and it explodes, right? So the pressure is going to increase. So here's what that means. That means that pressure is directly proportional to temperature. If my temperature goes up, my pressure is going to go up. Again, which makes sense. Again, this is called Gay-Lussac's law. Another great photo of good old Joseph Gay-Lussac. So here's some applications of that. Okay, if I take a can of hairspray, place it into a fire, again, what happens? Okay, it's going to blow up because that pressure that builds after that increased temperature, remember, if I increase my temperature, I'm increasing how fast my molecules move, causes them to move faster and faster. The container can't hold that pressure once it gets to a certain amount, and then all of a sudden, the container explodes. So, next one we're going to talk about, and the last one we're going to talk about, is volume and quantity. So we're going to talk about how those are related. So, as the quantity of molecules increases, what happens to the size of a balloon? So let's say that I had a balloon up here and I was blowing it up. When I blow air into it, what am I doing? Well, I'm adding more particles, right? So as I add more particles, what happens to the balloon? Well, it's going to get bigger, right? It's going to increase in size. So here's what that means. That means that volume is directly proportional to quantity. If my quantity goes up, in other words, if my number of moles goes up, then my volume is going to go up. Again, it makes sense. Add more particles, volume gets bigger. And this is called Avogadro's law. You've heard about him before. Avogadro's number, 6.02 times 10 to the 23rd. He also is the one who discovered this law. So here's some applications, okay? Let's say that we have a balloon. We've got it aired up. As we open up the balloon, right, we let some air out. Well, that's allowing gas particles to escape. As those gas particles escape, that means the molecules on the inside, right, the number of molecules decreases, which means the volume of the balloon is going to decrease. So whenever our quantity of molecules decreases, there's fewer molecules pushing on the outside of the balloon, meaning it's going to get smaller. So kind of here's a look at all those relationships. So Boyle's law was the relationship between pressure and volume. If I increase my pressure, well, what's going to happen to my volume? It's going to go down because as I push more on a container, it's going to push the molecules closer together, which causes the volume to get smaller. Charles' law is about how temperature and volume are related. If I increase my temperature, that's going to increase my volume because as particles move faster, they want to occupy bigger space. There's more collisions, so it's going to occupy a bigger volume. Gay-Lussac's law is the relationship between temperature and pressure. So as my temperature goes up, my pressure is also going to go up because of, again, more collisions happening. Avogadro's law is the relationship between quantity and volume. If I increase my number of particles, guess what? My container gets bigger, and that's something that really is something that you probably already knew a lot of these things. We're just kind of putting them in a more scientific way. So that's it for kind of the notes today. What I want you guys to do is answer these few questions just to kind of make sure that you know the information that you're supposed to know and to practice some of these relationships. Thank you for watching.